Hey, it's 4 o'clock, so let's get started. I'm excited to kick off this year's colloquium with today's speaker, me. And I'll be telling you about some of the things we've been doing here at Caltech using polyatomic molecules and exotic nuclei to explore fundamental physics. The universe presents us with a lot of very fundamental mysteries, many of which relate to its basic composition. About 70% of the universe is dark energy, which drives the expansion of the universe, and we have no idea what it is. About 25% of the universe is dark matter, which influences large-scale gravitational dynamics. We also have no idea what that is. The remaining 5% is matter, everything we know and understand, from atoms to planets and galaxies, but we actually have no idea where it came from. So, lots to figure out. What I mean when I say I don't know where it came from, brief version of our model of how the universe came to be is there was a Big Bang, which was a tremendous release of energy. E equals mc squared, that energy converted into mass, and as the universe expanded and cooled, it coalesced and formed planets and galaxies and everything else that we know about. But there's a problem with this explanation. According to all the laws of physics that we know, there's a symmetry between matter and antimatter. Whenever you create mass out of energy, you create equal amounts of matter and antimatter. But we don't see any free antimatter in the universe. If you want to study antimatter, you have to work very hard to make it in the laboratory. So something is breaking this symmetry between matter and antimatter that gave rise to everything we know in the universe. So there's some major source of asymmetry that we don't understand. And we don't know what this process was that made matter after the Big Bang, but we have some clues about it. We know it must violate fundamental symmetries, for example, mediated by some particle that couples to regular particles in a way that violates the matter-antimatter symmetry, which is called charge parity violation, this particular violation between matter and antimatter. This generates symmetry violating electromagnetic moments in regular matter. For example, permanent electric dipole moments or higher order electromagnetic moments in nuclei, some of which I'll talk about in a bit. And this enables the study of exotic high energy physics to probe these fundamental mysteries using small-scale tabletop experiments that only have to deal with regular matter like electrons and neutrons and protons. To see the relationship between these electromagnetic properties and symmetry violation, if you consider a particle like an electron or even something like a neutron or a nucleus, which has a spin, and you imagine that it has a dipole moment, which at least classically you can imagine as a separation of charges. If you look at this particle flipped in a mirror, when you look at the mirror image of something rotating, it's rotating with the same sense of rotation. So its spin won't change, but this spatial charge distribution, which gives rise to the dipole moment, will reverse. And so you'll end up with a particle that looks fundamentally different, and in fact, distinguishably different. If you had given me one of these particles and one of these particles, I could do experiments to determine which of these two particles you gave me. But we know that all electrons are indistinguishable. All neutrons, all nuclei of the same species are indistinguishable. That means that this mirror image particle can't exist. And so, for example, the existence of permanent electric dipole moments can only arise because of some, as I've shown here, parity violating or reflection violating symmetry. And you can make similar arguments to show that these moments violate a number of symmetries, including time reversal symmetry and charge parity symmetry, the type of symmetry that we're trying to explore to understand the matter-antimatter asymmetry in the universe. If you want to look for electromagnetic properties of particles, you want to put them in a large electromagnetic field to study how they respond. And it turns out molecules, polar molecules, have essentially the largest electromagnetic fields that you can find. The electric field inside heavy polar molecules can be up to 100 gigavolts per centimeter, which is around 1,000,000 times larger than fields you can create in the laboratory and is around 1,000 times larger than fields you can access in atoms. So we in the community call this molecular enhancement. And the idea is that these large fields amplify symmetry violating electromagnetic observables in electrons or in nuclei. So a classic experiment of this type would be take a molecule with a valence electron or with an interesting nucleus and reverse the direction of that spin relative to this internal field and see if there's an energy shift. Symmetry would dictate that these two levels would have to be exactly degenerate, but in the presence of these symmetry violating electromagnetic moments, there will be some energy difference between these states. They're very small effects, so you have to use precision measurement tools to search for these. And the challenge with these types of experiments is that you have to have control over all of the molecular quantum states. You have to be able to access and control these individual spins and change their orientations and read them out. And that's very hard to do. And it's because it's so hard to do, atoms, despite the fact that they are 1,000 times less sensitive, were actually the most sensitive experiments for decades, including going back pretty far before this graph starts, simply because the experimental tools to work with atoms were so much more advanced. In the early 2010s, molecule experiments surpassed atomic experiments, and since then there has been a fairly rapid increase in sensitivity, around a factor of 300 or so, since these experiments came online and are now probing the tens, almost 100 TeV scale for new symmetry violating fundamental particles and forces. In our group, we're interested in a few directions. One of them is pushing this sensitivity to higher and higher levels by using modern quantum tools, the types of tools that have been behind the very rapid advances in atomic quantum science, but have not yet been applied to any of these molecules, or even these atoms. And we also want to extend the molecular toolbox to explore the nucleus. So far, these molecular experiments have only explored for the electron EDM, electron symmetry violation. Exploring the nucleus requires a more complicated molecule. And that brings me to what I'll be telling you about today. In our group, we engineer molecules to use quantum tools for molecular precision measurement. We use those tools to study interesting nuclei and molecules, and then I'll provide some outlook of where we're going. So I'll start here with engineering molecules. So if we want to do an experiment, we have to pick a molecule. And one thing that we have is essentially a requirement for these types of experiments is you need a heavy nucleus. The sensitivity to fundamental symmetry violations scales very rapidly with the size of the nucleus. So you want to be as far down the periodic table, something as heavy as you can reasonably work with. If you want to use modern quantum tools, one of the ingredients that you would really like to have is optical control, meaning the ability to do high fidelity preparation and readout and measurements using lasers. But you also need to be able to suppress decoherence and errors, especially from electromagnetic fields. Polar molecules are very sensitive to electromagnetic fields, which is one of the reasons why a lot of people are interested in them. But for us, that poses a big problem. And it turns out in the simpler diatomic systems that previously had been considered for these searches, you can't combine both of these. You have to choose either one or the other. And so in order to do an experiment that combines both, we use the complexity of molecules as a resource to engineer the different degrees of freedom to give us these features simultaneously. So we can take some heavy metal nucleus, we can design a bond to give us good optical control, and we can design a ligand and symmetry in the molecule to give us good electromagnetic control over the molecule. And these are I'll walk you through these steps. So by optical control, what I really mean is the ability to scatter many photons, which is a very basic ingredient for a lot of atomic quantum science experiments to, for example, optically pump to prepare some state or to transfer population, or to scatter photons to detect fluorescence, to measure states. Or if you can scatter enough photons, since photons have momentum, you can apply forces, including cooling and trapping forces. So these are very basic steps in, say, atomic clocks or atomic quantum simulators or quantum information processors. But there's a potential problem, which is that if this excited electronic state decays into an unknown state that you don't have any control over, it's effectively gone. And that's a problem in molecules because this always happens in molecules, or at least always can happen in molecules, through vibrational excitation. If you excite some electron in a molecule, when that electron decays back to the ground state, the electron orbital changes, it kicks the molecular bond, and the molecule starts vibrating in a spontaneous and uncontrollable way. And it turns out there's nothing you can do to make this not happen, but you can at least find species where this is manageable, meaning it just doesn't happen very much. The types of species where this is manageable is molecules where the valence electrons don't participate in the chemical bond. So an example would be an atom with two valence s electrons, like something in the second column, bonded to, for example, fluorine. Calcium fluoride is a good example of this. Calcium has two valence electrons. The fluorine takes one. It is bound very deeply, so it's basically gone. And you end up with this metal-centered calcium electron, which you can very easily excite with a laser. And it turns out that this works if you swap out this fluorine for something more complicated like OH or even CH3 or NH2. And this is great. This is the way I think chemistry should work, that you can just approximate fluorine by something else. And it's basically the same. That usually doesn't work, but for these types of very uniquely bonded molecules, this actually works surprisingly well. And you end up with very similar structures in these more complicated polyatomic molecules. And if you do proper quantum chemical treatment of this, you find that indeed the electron wave function is really pushed away from the bonding region. So you get a good decoupling of the electronic and non-electronic vibrational degrees of freedom. And this idea of using molecules with this type of structure has been behind the very rapid advances in the last decade or so in molecular laser cooling, where the molecules that have been laser cooled and trapped have this type of structure. And so we're going to use this structure to realize optical control in our molecules. The types of atoms that give you this type of structure are shown here. If you want to do an EDM or a CP violation search, you want something very heavy, so you want to go as far down as you can. So ytterbium is a good choice. It's the heaviest stable atom that makes these types of molecules. It also has a fairly interesting nucleus, which is something I'll return to later. Radium is even heavier, but it's radioactive. So it's maybe not a good choice for a first experiment, but I'll say more about that later. So this is how we're going to get optical control. We also need this good electromagnetic control over the molecules. And that's a feature that we can get by using the polyatomic degrees of freedom and symmetry in the molecule. If you consider the rotational states of a rigid rotor, there's this alternating, the ladder of alternating opposite parity states in the rotational quantum number. If you lower the symmetry of the molecule, if you break the cylindrical symmetry of the molecule, you get a more complicated structure. For example, if you look at, say, a planar tetratomic molecule or a triatomic, which has a bending motion, which lowers the symmetry of the molecule, you now have access to two distinct moments of inertia in the molecule. And so you get two different rotational ladders with slightly different energy. So instead of a ladder of opposite parity states, you get a ladder of doublets, of two pairs of states, each of which have opposite parity. And this is useful. These are parity doublets, by the way, which if you've ever talked to me, I probably say that phrase a lot because I really like parity doublets. And one of the reasons I like them is because they give you a lot of advantages, but one of the advantages that's most relevant for EDM and CP violation searches is that you can polarize the molecule in much smaller fields. So in order to realize EDM sensitivity or CP violation sensitivity, or if you want to use these molecules as a qubit or something in a quantum simulator, you have to polarize them in the lab frame. And these lower symmetry molecules you can polarize in much smaller fields, say tens of volts per centimeter versus the several kilovolts per centimeter you'd need for a simpler molecule. And That's useful because it not only makes the experimental design much easier, but it turns out there are a lot of very dangerous systematic errors and effects that can creep in as you apply a larger and larger field. So avoiding this is really, really useful. And intuitively, the reason why you get this additional level of control is, the molecules want to rotate. They're rotating. And if you want to align them in the lab frame, you have to apply a large enough electric field to overcome that rotational energy. And in a rigid rotor diatomic, that means you need a fairly large field. In these more complicated lower symmetry molecules, you only have to apply a field that's large enough to overcome this moment of inertia difference between these two symmetry lowered states, which is much smaller. So you can align them in relatively small fields. So this is what we're going to use to realize electromagnetic control in these molecules. So we mostly work with YbOH, ytterbium monohydroxide, and more recently with radium OH. We choose OH mainly because it's the simplest polyatomic ligand that gives us all the features we want, including this bonding for good optical control. They're heavy, so they have good CP violation sensitivity. They have this highly polarizable polyatomic symmetry lowered structure. And then it has some additional, these molecules have some additional features which at the time, when we started these experiments, we didn't really realize, but eventually we figured out. They have in situ tunable properties. So for example, you can, just by changing an electric field in the lab, you can change the magnetic properties of the molecule. And they also both have interesting nuclei, but for different reasons. And I'll say more about these later. So that's how we designed these molecules that we wanted to work with. And ultimately, we want to do measurements. But one of the downsides of working with a new molecule is that there are some intermediate steps that you have to go through. And I won't say too much about these steps. I'll just give you maybe some of the highlights. So first, we have to figure out how to produce these molecules. These molecules have unpaired electrons. They're extremely reactive free radicals. They react essentially instantaneously with everything, so you can't really buy them. You have to make them in the apparatus where you want to measure them. And they also must be cooled to cryogenic temperatures and in the gas phase if we want to use the precision measurement tools that we are interested in using. So we use a technique which is now a fairly standard one called cryogenic buffer gas cooling. So we make the molecules in a 4 Kelvin helium gas, say from some solid precursor containing the atoms that we want to form into our molecule. We ablate or vaporize with a pulsed laser this solid precursor to make some hot gas phase molecules. They're then cooled by colliding with this cryogenic helium. They don't react with the helium, and then you can study them directly in this gas cell, or you can form a beam out of them to send them to some other detector or measurement device. This is a common tool these days for molecular precision measurement and laser cooling experiments. And it's nice because it works for basically anything. It works on atoms. It also works on even large molecules, like whatever that is, and everything in between. But there's a little bit of a catch because this is all happening at 4 Kelvin. A lot of the chemistry you would want to happen to make these molecules is frozen out. So when you do this ablation of the solid precursor, you actually mostly just get a bunch of atoms. So you mostly get a bunch of ytterbium, and maybe you get some other things too, but ytterbium can't really react with anything at 4 Kelvin to make YbOH because there's a large energy barrier, much larger than 4 Kelvin. So what we do is we excite the ytterbium atoms resonantly with a laser to an internal state that has enough energy to overcome these barriers. So then we can get rapid formation of YbOH or other molecules. When we do this, we generally get around 10 times more molecules. And this is an approach that works for many different species that we've now made a few different molecules using this approach. So now we can make them. We have to study their basic properties by doing spectroscopy. YbOH had effectively no previous spectroscopy. There was actually one paper written about it maybe 25 years ago, which turned out to be wrong, but luckily in a way that basically didn't matter for us. So that means we have to measure all the levels, transitions, couplings, electromagnetic moments, everything in this molecule, which is hundreds of different things, including some previously unstudied structures like these symmetry-lowered states in molecules hadn't yet been studied to the degree to the precision that we would need to understand them. And I won't go over all of this, but we did all these measurements. It took a few years to do this, which is fairly common for these molecular precision measurement experiments. If you'd like to know more about this, I'm happy to talk about this at the Wine and Cheese for as long as you're willing to listen. And we had fun doing this. Spectroscopy is fun, but it's not really our goal, and it's very time consuming. So we recently developed a new approach which we think will speed this up a lot, so we don't have to go through this again. We can now measure strong transitions. For example, the calcium fluoride, one of the laser cooling transitions in calcium fluoride, we can measure its spectrum in about 1 second. And with a few hours of averaging, we can measure hundreds of lines in many different molecular bands. And the hope is that we can turn this spectroscopic characterization of molecules like this into something that should just take days. But we figured that out too late for YBOH. So we've done all that preparatory work, so now we can move on to measurements. So the way we do the measurements in the molecules is different than had been previously done. So we want to do, in an idealized picture, we want to say, look at two states where the electron or the nucleus is flipped and see if there's an energy difference. And so, okay, molecules have more than two levels. Maybe they have a structure that looks like this, say in some particular hyperfine level. And what we do instead is we identify these two states with two states in the molecule that are separated by some energy difference, say some hyperfine energy. We can then measure that energy difference and do a frequency comparison, like a clock to a frequency reference. And this approach works very well in especially complex species, which these molecules certainly are. There's a big problem to this approach, which is that these transitions in molecules, and molecules in general, are very sensitive to electromagnetic field noise and errors. So in order to make a good clock, you don't want something that's just picking up a bunch of noise from the environment. And this is especially a big problem in polar molecules with an unpaired electron, like these. But we can use some unique advantages of these molecules to make this a practical approach. We can measure all of these transitions and compare them to a clock to, say, get rid of a lot of common mode errors. But also there's a unique property that with polyatomic molecules in these symmetry-lowered states, you can actually tune the properties of all these transitions, in particular their electric and magnetic response. And so you can make the transitions very robust noise and therefore good clock states. So in polyatomics, we realize tunable electric, magnetic, and CP violation sensitivities in situ with applied fields. Just by varying applied fields in the lab, we can make EDM clocks in the molecules that are insensitive to fields, but very sensitive to CP violation. But we can also make field sensing transitions that are very sensitive to fields that we can use to map out the fields very precisely. So this is an example of some of these states transitions that we characterized in a recent experimental paper in YBOH in some moderate electric and magnetic field values, but a large enough electric field so that we realize we polarize the molecule and realize large EDM sensitivity. These two states become a clock transition because their field sensitivity vanishes, but this state maintains very high field sensitivity. And so this approach is fairly generic in polyatomic molecules with these symmetry-lowered states. Although this is an example that we worked with experimentally quite a bit. What we do in the lab to study these is we take our YBOH beam, cryogenic molecular beam, and we send it down some beamline containing electric and magnetic fields and a lot of laser access. So we optically pump the molecules into one of these two clock states that we want to characterize. We do a coherent 2-photon pulse to make a superposition of these two states. We let them interfere with each other, and then we apply another pulse to map the phase onto population, and then we scatter photons off the molecules to reconstruct the population and therefore the phase. So it's a fairly standard Ramsey type measurement if you're familiar with those, and we can see the characteristic oscillations or Ramsey fringes from these states interfering with each other. And what we find then by looking at how does this interference respond to the application of fields, we showed that you can indeed directly suppress the electric and magnetic sensitivities simultaneously by a factor of a few hundred. Probably it's lower than that. We were limited in our the ability of our statistical calculations to determine how low it actually was. But we can independently set the electric and magnetic field shifts, including to 0 and including changing the sign. And this is a useful tool to suppress decoherence and detect and suppress errors, especially in these types of molecules and these types of experiments. Errors arising from field imperfections are the #1 problem. And so we can, for example, operate our experiment normally here, where the dipole moment, the effective molecular dipole moment or electric field sensitivity and magnetic dipole moment or magnetic field sensitivity are 0. But we can then turn a knob and change the molecular dipole moment. We can make it positive or negative, and same with the magnetic dipole moment. So this gives us a lot of control over these molecules that you can't realize using other approaches. So for example, if you turn this field sensitivity really high up to a really large value, you can sense the fields directly by observing the large shift in response to, say, a purposefully applied magnetic field error. Then, if you want to do your measurement, you turn the field sensitivity back off, again, just by changing a field in the lab, a static field, and then you can do your measurement in a way that's very robust against field errors and imperfections. You can also use this reduced sensitivity to fields to make your system very robust against noise. So you can apply, for these field insensitive measurement states, you can apply large values of magnetic field noise before you start decohering the state. Whereas in a typical sensitive transition, this would decohere almost immediately because of this unpaired electron in the molecule that makes it very sensitive to magnetic fields. But we can sort of turn that on and off in these types of molecules. And there's an intuitive picture of how this works, why just adding an electric field or a magnetic field can change the electromagnetic properties of the molecule. And it's due to some interesting couplings between the different motions in the molecule. So these molecules have an unpaired spin, which gives you your magnetic sensitivity. They have an electric dipole moment, permanent electric dipole moment in the molecular frame along the symmetry axis. But they also have the possibility, because they have more than 2 atoms, this hydrogen atom, for example, can orbit around the symmetry axis. And when that happens, that makes an internal magnetic field in the molecule, which interacts with this spin. So it gives you a coupling of the form that looks like this electron spin interacting with this rotational motion of this hydrogen atom. But that means when you change the electric field in the laboratory and you change the orientation of the dipole moment in the lab, you can find magic angle type conditions where the coupling of this electron spin to this internuclear axis, which is the axis along which this magnetic field lies, and the precession of this internuclear axis around the lab frame cancel out. And so you find then that the electron spin is always perpendicular to the lab fields, and it becomes magnetically insensitive. So that's how we realize these types of conditions, by using the lower symmetry and additional complexity in these molecules. And importantly, we don't get rid of the sensitivity to the physics that we're interested in. The CP violation sensitivity comes from the interaction of the, for example, electron spin with this internal electric field here along the symmetry axis, which is not zero in this condition. And in fact, it's essentially about the same size as it is in any other condition. So now we have these tools, and we're interested in using them to probe interesting nuclei. One of the things that we're currently focusing on is an MQM search in 173 YBOH, so different isotope of ytterbium, which is still stable. MQM is a magnetic quadrupole moment. It's a symmetry violating magnetic moment, which unlike a dipole moment, an electric dipole moment, which is a separation of charge, a magnetic quadrupole moment is a separation of current. And this can happen in nuclei due to nuclear effects like nucleon EDMs or quark EDMs or symmetry violating nuclear forces. So it gives you access to different types of physics than you can access, for example, with the electron EDM. And in the ytterbium 173 nucleus, there's an additional enhancement in sensitivity to this effect due to the fact that it has a quadrupole shape deformation. So it's a good nucleus for these types of searches. And in fact, this was the original motivation for developing this clock approach, because the structure of this molecule is extremely complicated. This is just one rotational level. This is all the hyperfine structure in one rotational level of 173 YBOH. And doing a traditional Ramsey type spin precession measurement, or the types of measurements that people have done in molecules like this previously, is essentially impossible. But this clock approach works well. And so we can see coherent oscillations and interference between MQM sensitive states in this molecule, similar to the method that I was talking about before for the electron EDM. And these days, our current focus is on improving the resolution of our measurement. So this was the oscillation I showed earlier as of last week or maybe the week before. These fringes, this oscillation is now much faster, much sharper. So we can get much better resolution, which we achieved by extending the coherence time of the molecules by a factor of 30 or so. Looking to even further deformed, unusual nuclei, nuclear symmetry violations are enhanced even more in heavy octopole deformed nuclei. So nuclei that are shaped like this, which some actually are, like radium. And these enhance nuclear symmetry violating effects by around a factor of 1,000. These combine with the molecular enhancement that you get from the large internal fields. And so if you combine, say, some heavy polar molecule with an octopole deformed nucleus, you can realize very large gains in intrinsic amplification to these symmetry violating effects. The amplification is so large that even if you could control just one molecule at a time, you would be probing the frontier of hadronic symmetry violation. The challenge is that these nuclei are radioactive and rare and very hard to work with. So even realizing an experiment with one molecule is still currently out of reach. But enticed by the opportunity to get these very large enhancements, there are a large number of efforts around the world now, around 24, to study radioactive molecules for a number of reasons, not just symmetry violation. There are a lot of interesting things you can study using radioactive molecules. Most of them are just starting or haven't started yet, and there are several large facilities and international collaborations working on this problem. One of the important experiments that's ongoing is this molecular beamline at CERN Isolde, which is the only other operational radioactive molecule experiment, in addition to the one that I will tell you about shortly, where they used the CERN proton synchrotron booster to ultimately make a beam of radium fluoride molecules at 40 keV and do laser spectroscopy a few years ago. If we want to use our tools that we've been developing for precision measurement, these start at much lower temperatures. These start at like milli-EVs. So say to use a beam experiment like we've been doing with YVOH, or like the ACME experiment uses, or laser cooling and trapping. They start from these much lower energies. And so our approach is to introduce these exotic nuclei directly into molecular precision measurement experiments. So directly into these cryogenic sources for then beam formation or laser cooling or loading into ion traps. And this approach is nice because it's applicable to essentially any species as long as you can get it and efficiently handle it. And it's a tabletop approach. If you go back to the which species should you use question, these are the nuclei that are heavy and octopole deformed. So they're all radioactive. They're all hard to work with. If you want to use the tools that I've been talking about, these molecular quantum tools, that's these again. And there's this interesting case where they overlap, which is radium. And so we're interested in studying radium containing molecules in our lab for this reason, that we can combine all of these different tools that I've been talking about. Our first source of radium was watch hands, for those old hand-painted radium-containing watch hands, which you can buy on eBay. This actually worked. It didn't work. The watch hand to watch hand variations are sort of significant, but generally there's not a lot of radium in these, but it was enough to see something. A more science-y approach that we ended up settling on after showing we could do some basic things was we procured 1 milligram of radium salt from the Department of Energy. 1 milligram of radium is actually a really scary amount of radium, and so we divided it into smaller quantities. It was also very expensive, so we divided it into smaller quantities, 50 microgram quantities that we could use for individual runs with help from our friend Alyssa Geiser, who's a radiochemist. We then take this radium, we use some secret sauce to make a solution which we can then deposit onto a substrate to make a uniform, repeatable, stable matrix containing these radium atoms that survives at cryogenic temperatures, which we can then ablate or shoot with a pulsed laser to vaporize some of the radium. And we find that we get effectively order unity material conversion, which is really important because you can never get a lot of these isotopes. And by the way, Caltech has an isotope lab, which was really important to allow us to do this work. And it's a very unusual resource for a university to have, although not as unusual as radiation safety people who you actually want to be with you when you do this stuff because they're really great to work with. So we take this radium goo and we attach some other materials nearby that have atoms we want to react to make our molecules. So like fluorines or OHs or ODs. We then install this in a cryogenic buffer gas cell. We ablate the radium along with whichever species we want to react to make the molecule that we want. And all of this is happening in this tabletop chamber. We always say we do tabletop physics. This is the only apparatus we have which is actually on a tabletop in its entirety. It's in Downs. Come check it out if you're interested. We then do, after ablating, we do this same trick driving radium to its excited state to overcome chemical reaction barriers and make resonant increased production of these radium molecules when we're hitting this resonance in the radium atom. And for these types of experiments, this is a big advantage because usually these isotope experiments have to be really careful about purifying and isolating and getting rid of contaminants. But we don't have to worry about that at all. We make the molecules on demand when we need them. And in fact, currently already the radium is basically a trace impurity in this matrix. We can then send a scanning resonant laser through, scatter photons off of the molecules, and detect them with a photomultiplier tube and see with a single pulse and creation of molecules, we can detect the fluorescence in a single shot and measure the properties of these cold radioactive molecules. Another downside of these really heavy species is the theory is very hard. Using even state-of-the-art relativistic ab initio methods, our collaborator Lan Cheng at Johns Hopkins was only able to tell us the wavelength of this transition, or the frequency of this transition, the electronic transition we wanted to excite and study, in radium OH to about 10 terahertz, which is very large compared to the resolution of our instrument. And the usual approach of just scan until you find something doesn't work because we have so little of this material. So what we did was we took a phased approach, starting with a broad laser, a spectrally broad laser that was about 40 gigahertz wide, so that we could carve out large swaths of this uncertainty region in actually only a few hours with 10 micrograms of material. We were able to find something that looked like a resonance. The key innovation to this was to use a piece of junk laser that we bought off of eBay, which was so terrible that Caltech magazine wrote an article about it. So you can read this article if you want to learn more about how we did this. Once we find the transition to this resolution, we can then go in with a higher resolution, more modern laser, scan it, start to see things that look like molecular features, and then we can pick these features and go study them with a nice single frequency tunable good laser, and get very high quality measurements of the properties of these cold radioactive molecules. So we've taken measurements of a few different molecules, 3 different molecules in this apparatus. This is the first production and measurement of cold radioactive molecules in the laboratory. It's also in a cryogenic buffer gas cell on a tabletop, so it's the same starting point as laser cooling and precision measurement experiments. And so we're excited about pushing these molecules into that realm. To get started in that direction, we've been recently, like in the last few weeks, studying the main laser cooling transition in these molecules. We have preliminary observations that look like photon cycling, so the ability to do the basic ingredients of this optical control in radium fluoride. We're interested in radium-226 for electron EDM searches, but for nuclear EDM searches, we are interested in radium-225 or 223, which are shorter-lived isotopes. We can just drop them into the apparatus and make these molecules, but the challenge is getting these isotopes is very hard. You can buy them from the DOE. You can also make them locally with radioactive cows, which is a technical term for just some other material that decays into these that you can then chemically extract. So you can sort of milk the radium out of this. I didn't come up with that. We're also implementing this approach at some of these beam facilities that have access to even more exotic nuclei. We're also a member in the newly formed RAX collaboration to laser cool radium molecules for precision measurements. This is a collaboration between myself, John Doyle at Harvard, Ronald Garcia Ruiz at MIT, who was the guy behind the CERN-Isolde radium molecule work, with support from EFRIB, and we're currently commissioning a molecular beam to do this work. Ultimately, we want to do these, especially in radium, these experiments in a trap. So a few years ago, we did a demonstrator or pathfinder experiment in CaOH, calcium OH, in collaboration with John Doyle's group at Harvard. Calcium is too light to have any EDM sensitivity, but it has the same structure and properties, these symmetry lowered states, as heavier molecules like RaOH. So starting from ultra cold, laser cooled and trapped CaOH at tens of microkelvin, performed a measurement to create a coherent spin superposition of these EDM sensitive states, which you can then see interfering as they evolve coherently. And we were able to show that this ability to tune the magnetic properties of this molecule in particular were very valuable. So this again is showing this direct measurement of tuning the magnetic response of the molecule and making it very close to zero. And practically, this means if you say operate your experiment here with a typical value of magnetic sensitivity for something with an unpaired electron, you get some coherence time. If you just change the value of the electric field, you extend this coherence time rather dramatically. And we were able to observe up to 30 milliseconds of electron spin coherence time in a chamber that had no attempt to protect the molecules from noise. So there was no shielding. It was made out of stainless steel. And with just some very standard tricks to reduce the magnetic noise, we think that you can push this fairly straightforwardly to the second scale and beyond to do very long coherence time, very sensitive measurements. So where are we going? What's next? So we're continuing our MQM measurement, especially improving the resolution, and then moving on to careful systematic error characterization. We want to pursue these precision measurements in ultra-cold radioactive molecules, including the spinful nuclei of radium. We want to explore other exotic nuclei. Radium is really interesting, but it turns out that there's basically no data about radioactive molecules more or less at all. There are a lot of interesting applications in nuclear structure or chemistry or astrophysics that you could access simply by being able to make and study these molecules in the lab, which we are now in a unique position to do. We're interested in studying new molecular structures. So these metal OHs have served us well, and they have a lot of great features, but there are more complicated molecules and structures that we know have additional advantages, but we just don't know enough about them yet. And we're starting to study them. And looking further down the road, we're interested in developing and using tools like quantum enhanced metrology or advanced cooling and trapping to continue improving these experiments. So I think it's an interesting time to be in this field as we now start to access these different tools to increase the sensitivity and start exploring different areas. And to give you an example of why even these really optimistic projections are maybe believable. If you consider an experiment with 1 million molecules, 100-second coherence time, with a heavy deformed nucleus and good quantum control and robust error rejection, each of these things has been achieved in an at least comparable system. Combining them all will be certainly non-trivial, but there's a growing community trying to realize experiments like this because the payoff would be fairly large. You could access beyond the PeV scale for CP violating physics at 1 loop, or beyond 100 TeV scale at 2 loop, reaching very high sensitivity for both in the lepton and hadron sectors, and in fact even getting close to the standard model CKM values. And in timescales that are maybe short enough that hopefully I and all of you could enjoy them as well. And then maybe even future improvements from things like more speculative things like quantum enhanced metrology or highly exotic nuclei that have even larger enhancements beyond radium. So with that, I will thank my group who did all the actual work and our great collaborators and former group members and funding sources that helped make all this happen. And thank you for your attention, and ask if you have any questions. Yes.
So for those standard model predicted values, which you said are reachable in 10 to 20 years, say, by combining all the ingredients you described, is that something you can envision doing in a single investigator lab on the scale of yours, or will it take a much larger scale experiment?
I think it would probably be a few PI scale experiment. I think a lot of most of the difficulties would be on the laser cooling and trapping and quantum science side of this. But that field is advancing very rapidly, mostly from just single PI groups. So I would guess that this would be a few PI thing, sort of like the ACME or JILA collaborations. because I don't know that you need a big gigantic team to do an experiment like this. Yeah. Any other question? Oh, yes.
I want to make sure I understand. You polarize those molecules such that the molecule points in the direction of the electric field in the left.
Mhm.
And you also need to control the rotation of the hydrogen.
Right.
Do you also make it rotate in the same direction, or do you distinguish between different rotational states by polarization or something?
Exactly. It's by polarization. So we don't do anything to sort of make the hydrogen rotate in one way or the other. We just tune our lasers using polarization or energy shifts to address whichever state has the hydrogen rotating in whichever direction we want. So really the only external knobs that we use are external static fields and then the lasers. You know, the lasers where we can control both the polarization and which states we're addressing.
Do you use magnetic? External magnetic?
We do, for example, in this, for these clock measurements, you don't have to use a magnetic field, but for this particular experiment, we did, because at least this transition that we were studying had these interesting properties at a finite magnetic field, which was 12 milligauss. But you can find conditions like this where you don't need a magnetic field. But we chose this one because this one had really, really nice properties just experimentally in terms of laser access, laser polarization, sensitivity, how bright the fluorescent signal was, things like that. But for example, in the CAOH work, there was no magnetic field applied. Or it was, attempts were made to make it as small as possible, canceling out, say, Earth's field.
So the control is a quasi-static reduction of susceptibility to external fluctuations rather than dynamical control. Is that correct?
Yeah, it's just static fields.
Yeah.
That's it.
What major sources of noise in your experiment that you have to contend with? Like I know for electrostatic traps, fluctuations of random molecules that are on the surface of the electrodes and so on. But you're separated because you're doing all this optically, right?
Right. Yeah. So the two biggest sources of problems, at least for neutral experiments, for electric fields, it's the fact that you always have dielectric gunk on your electrodes. So there's always some uncontrollable, slowly drifting offset field that there's nothing you can do about. And then for the magnetic fields, it's the fact that when you usually with these experiments, you have magnetic shielding, but the magnetic shielding is nonlinear and there's always some remnant magnetization and there's nothing you can do about it. So there's always some background slowly drifting magnetic field as well. And so for these types of experiments, usually the actual noise is very well under control, but it's slowly varying small DC shifts which give you systematic errors that might mimic the signal you're looking for. That's the real big danger. Yeah. But as we push these to longer and longer coherence times, then the electromagnetic so a lot of the reason that that the noise itself hasn't been a problem is because a lot of those experiments that I showed on that plot didn't have very long coherence times. There was one exception, which was the hafnium fluoride plus experiment had a long coherence time, but usually these experiments have a short enough coherence time that the experiment's over before you decohere anyway. But as we push these to longer and longer coherence times, that ability to get fine control over the decoherence will become very important.
You do not answer the questions of one another, but you talk about a bunch of different directions, EVMs, magnetic molecules. If you have to bet on something, or if you run out to only use one approach, find beyond the standard model physics, Which one will it be?
Yeah, so I'd say, and in some sense, this is a future version of all the things we're working on. I would say it's these radioactive molecules, ultra-cold radioactive molecules and traps. Because, for example, this is actually really MQM sensitive. And so we would be able to improve, like the future generation MQM measurement would be this one. And I think that yeah, the ultra cold radioactive molecules and traps. And there's a lot of groups that are starting to pursue that now for that reason, that it appears to combine this really huge sensitivity boost with the ability to get long coherence times and really good control. And so I think that's the area that's going to really push these limits down by a lot.
For the connection to high energy physics, how much of that is known or unknown due to the nuclear physics side of it? Like, is that limited by our understanding of the nuclear physics or of the
Yeah,
just the symmetry breaking is enough?
good question. So yes, just the symmetry breaking is enough, because if you see, assuming that you haven't been fooled by a systematic error, these effects are intrinsically symmetry violating, whereas no molecular or nuclear or anything background will give you a CP violating erroneous signal, unless it's actually CP violating. But in terms of interpreting, going from, one day we measure the MQM or a nuclear shift moment or something to be this, what does that mean in terms of like the mass of the particle? There's actually a lot of nuclear physics uncertainty. It's basically order unity uncertainty. The atomic and molecular uncertainty, like how big are these effects amplified in the fields, that's actually very well understood. But going from, say, the 173 ytterbium magnetic quadrupole moment is this to some CP violating pion coupling is this, is basically order unity uncertainty. But there's been a lot of work to improve that, I think spurred on by the fact there are a lot of groups now getting into these nuclear symmetry violation experiments. And so people are extending like ab initio methods to heavier and heavier nuclei. And so getting better measurements, better theory values for those, I think is coming. But it still wouldn't change whether you have a signal or not, but it would absolutely change your interpretation of that signal.
I imagine detecting the state of the molecule is probably more challenging than an atom. As you go to more and more exotic molecular structures, bigger molecules, you anticipate that the current toolbox for detecting molecular states would still apply, or do you additionally have to keep that
We're mostly interested in structures where you can still do this optical control, which not everyone is pursuing that route, but all of the molecules that we consider, like this one, are ones that we predict should have the ability to do this optical control. Just because it's such a valuable tool, it seems really hard to give up. But there are people pursuing other avenues where you don't need that optical control. You get it from something else. But that's exactly what I mean when I say we're sort of exploring these new molecular structures, is like, where else can you get this type of optical control? Well, it's 5 o'clock. Please join me for the wine and cheese, and I'd be happy to keep talking with you. And thanks again for your attention.